In this video, we're going to be working BC Homework 5.4, which is about L'Hopital's rule. And so this is if we're confronted with a limit whose numerator and denominator are both going to 0 or both going to infinity, we can try to evaluate that by looking at the limit of the ratio of the derivatives of top and bottom. No quotient rule. Okay, but we have to be very careful with how we display our answers for this in AP Calculus, right? Because we want to get our justification points. So I'm going to be modeling that throughout this whole video, showing our work the proper way, maintaining limit notation, not saying anything that's untrue. Okay, so the first one, I'm going to zoom in a little bit. Limit of e to the 3h minus 1 over 2h as h approaches 0. Okay, I'm kind of looking at this, I'm seeing the denominator is approaching 0. I'm probably going to need to use L'Hopital's rule. So I'm going to check out the limit of the numerator. That's going to be 0. The limit of the denominator, also going to equal 0. That's when I need to use L'Hopital's rule. Okay, so, you can use L'Hopital's rule if you want, but if you write that, you're going to write that more than 19 times over the course of this homework, and so I'm just going to kind of save myself the effort. Rather than writing use L'Hopital's rule, I'm going to use L'Hopital's rule. So I'm going to kind of separate my work and take the derivative of the top and the derivative of the bottom, and then reconsider that limit as h approaches 0. The derivative of e to the 3h is going to be 3 times e to the 3h. Then the derivative of the negative 1 is going to be 0, and the derivative of 2h is 2. Okay, as h approaches 0, the numerator is approaching 3 times 1, the denominator is approaching 2. This is a good thing for me, right? I know that means my limit is going to be 3 halves. Okay, I can move on. Okay, number 2. This is a limit we already know how to do. And if you already know how to do this, okay, remember limits as x approaches infinity, if you just know what they're going to be, you are clear to just write down the limit. Okay, but in case you were wondering, like, wait a second, why was that actually even true in the first place? We could use L'Hopital's rule. Think about the limit of the top. The numerator is going to infinity. The denominator is also going to infinity. This is a situation we can use L'Hopital's rule on. So we're going to use it. We're going to take the derivative of the numerator and the derivative of the denominator separately, and we would get 3 and a 4. Okay, so I'm taking the limit of 3/4 as x approaches infinity, and 3/4 is going to stay 3/4, and that's just going to be 3/4. Okay, and that's another reason to believe me when I told you that this limit was 3/4 back at the very beginning of the course. Okay, but once again, just to reemphasize, if you just see that and you want to just write down equals 3/4 and move on, that would be totally understandable. Okay, number 3, and I'm glad I've got this one right here, very close to the beginning. Just to remind you that L'Hopital's rule isn't always necessary, right? Sometimes in AP Calculus we see limit questions like this. Limit as a approaches 1 of a squared plus 1 over 2a plus 1. And I think if you had taken the derivative of top and bottom preemptively, just been like, oh, this is L'Hopital rule homework, I'm just going to take the derivative of top and bottom, you would get the wrong answer. I've actually graded one like that in the summer, where it was like kind of a fake L'Hopital rule question, and you would be surprised the number of students that don't even really check the limit of the numerator and denominator and just jump straight to the limit of the ratio of the derivatives. And that's not the right thing to do. We got to check the limit of the top and the limit of the bottom. Okay, so the limit of the top is looking like 1 plus 1, that's going to be 2. Okay, already I know this is not going to be a L'Hopital rule situation, because it's if the numerator and denominator are both going to 0 or both going to infinity. Okay, the denominator is going to be going to 2 plus 1, that's 3. Okay, well that just tells me that this limit is going to be 2/3. Okay, and we can display our work the same way if we like, or we can just see that that was going to happen, and we probably could have just written equals 2/3 off to the side on that one. Okay, number 4, theta squared over cosine of 3 theta minus 1. When I see that theta squared, I'm a little concerned. This might require 2 iterations of L'Hopital's rule. And if it does, that's not the end of the world. I'm going to show my work properly. I kind of think that, because the justification standards are pretty strict for AP Calculus, that if you're going to see this on the free response, it would and they were going to grade it really strictly, it would probably be only 1 iteration, but it's definitely good for us to practice those ones that need more than 1. Okay, so I'm thinking about the limit of the numerator. Theta squared, as theta goes to 0, that's going to be 0. Okay, and the denominator, cosine of 3, 0. Okay, that's cosine of 0 minus 1, yeah, that's going 0 as well. Okay, so I'm going to apply L'Hopital's rule. I'm going to take the derivative of the numerator and get 2 theta. The derivative of the denominator would be negative 3 sine of 3 theta. Okay, and yes, again, I'm going to get 0 and 0, so I'm just going to do the same thing. I'm going to consider my limits separately. I'm not going to be drawing like an arrow to an illegal fraction or equals an illegal fraction. We're not doing that, right? We're allergic to those illegal fractions in this class. Okay, we can talk about them. Maybe we can say them out loud. You won't hear me saying it out loud. but we are definitely not going to be writing those illegal fractions. We are evaluating our limits separately because we're interested in getting the points, right? And then the limit of -3 sine of 3 theta equals 0. So I'm going to need to use L'Hopital's rule again. And so I'm going to take the derivative of the top and the derivative of the bottom, and I'll get 2 in the numerator and -9 cosine of 3 theta in the denominator. And then as theta approaches 0, okay, the numerator is going to 0, the denominator is approaching -9 times 1. That's going to be 2 over -9. Okay, you can barely see that. Okay, now number 5, the limit as t approaches 0 of sine t over t squared. Here's another one. I think this one's also going to require, no, this one is not going to require 2 iterations. This one's just kind of a letdown. Okay, so sine t is approaching 0, t squared is approaching 0. Okay, and it's like, okay, this looks like L'Hopital's rule, so I'm going to take the derivative of top and bottom. I'm going to be left with limit of cosine of t divided by 2t. T is approaching 0. Okay, and with this one, the limit of the numerator is 1, but the limit of the denominator is 0. And so that means we're getting closer to non-zero over 0, and that is the type of limit that just does not exist. So we're just going to say D and E, and that'll be all for that one. With number 6, okay, I'm looking at this, I'm saying, yeah, the numerator and denominator are both going to be going towards 0 as x approaches 1. So I'm going to write out my limits separately. The limit as x approaches 1 of e to the x minus e is equal to 0. And the limit as x approaches 1 of 5 log x is going to equal 0. So I need to apply L'Hopital's rule. I'm going to take the derivative of the top and the derivative of the bottom and try them out. The limit as x approaches 1 of e to the x divided by 5 times 1 over x. That would be e divided by 5 times 1. Okay, well, that'll just be e divided by 5. And then for number 7, okay, I'm looking at this. I'm seeing log of 1 is 0, -1 plus 1, that's 0 in the top, 1 minus 2 plus 1, yeah, okay, I'm going to get 0 for both. Okay, so I'm going to check those out. Definitely show that I know that the limit of the numerator and the limit of the denominator are both equal to 0, so I'm going to apply L'Hopital's rule, take the derivative of log t minus t plus 1, get 1 over t minus 1, take the derivative of t squared minus 2t plus 1, and get 2t minus 2. And then I look at those, and these are both also going to 0. So I'm going to say, all right, well, the limit as t approaches 1 of 1 over t minus 1, that's going to be 0, and the limit as t approaches 1 of 2t minus 2 is also going to equal 0, so I need to use L'Hopital's rule again. And so I'm taking the derivative of the numerator and the denominator, and, you know, I think something that might actually help me a little bit when I'm going about that process would be to think of that fraction, that 1 over t, as t to the negative first power, right? We don't want to unnecessarily use the quotient rule. You know, we don't have to for 1 over t. Its derivative, that's just going to be negative t to the negative 2. So I take the derivative of top and bottom, and I'd get negative t to the negative 2 divided by 2 as t approaches 1. I've got, okay, multiplication, or exponents before multiplication by -1, right? So I'm going to plug in that 1. I'm going to take 1 to the negative 2 power. Any power of 1 is 1. So I got -1 times 1. That's -1 in the numerator. 2 in the denominator. That's -1/2. Okay. And then number 8, this is one that I actually, I'm showing in the lesson now that L'Hopital's rule is not always the way to go. But I think that this one, there's a little bit more nuance to it. So I'm glad it's still in the homework, and maybe I'll give a little more detail. So the thing about secant and tangent, it's like, oh yeah, those are going to infinity as x approaches pi over 2, right? And that's not entirely true. I might say it does not exist. Right? If you think about tangent, or even secant being 1 over cosine, they're kind of approaching infinity from one side and negative infinity from the other side. And I don't think that that's necessarily the reason why why L'Hopital's rule doesn't work on this one. But I am just going to point out that this limit doesn't exist, that limit doesn't exist, and the way that you would actually compute this limit would be to, kind of take it from a pre-calculus approach, use some trig identities. So we're just going to rewrite this limit. Think about secant as 1 over cosine and tangent as sine over cosine. Okay, and then it's like, oh, okay, yeah, there's going to be some fraction arithmetic involved in here. We're going to say, okay, 1 over cosine, flip and multiply by cosine over sine. Kind of cancel off the cosines. Oh, yeah, sine of pi over 2, that's 1. And so this limit is going to equal 1. Okay, which is not to say dne over dne equals 1, but this one, L'Hopital's rule was not going to work. And I hope maybe, if you tried it on your own, that you saw if you try to do L'Hopital's rule, you kind of ended up very similarly to where we started, and that could be a frustrating thing. If you did it a second time, we would end up right back where we started. Okay, so I think just leave that one there. That's not really the type of problem you're going to be seeing in AP Calculus, but the type of problem I got to show you. Okay, so number 9, limit as x approaches infinity of x squared e to the negative x. Okay, well, that's not a fraction, you might be thinking. It's like, well, e to the negative x, we can write that as a fraction, so we're going to rewrite it. Limit as x approaches infinity of x squared divided by e to the x. And this is another one that I have been showing in the lesson, in recent years. So I'm just going to say, okay, I've already showed you why, you apply L'Hopital's rule twice on this one. You see you get something that's constant in the numerator, growing in the denominator. That's exactly what we say goes towards 0. And in AP Calculus, you do not have to justify your answer for something like this. You say that limit is 0. No reason really needed. Okay, and I'm going to save the time and energy because we're going to need it for number 10. This one's really long. This one's going to require, I think, 3 iterations of L'Hopital's rule, which is definitely more than I would ever ask you to do on a quiz or a test. But this one's a good one. It's maybe good for us to do it once or twice on the homework, right? Test the limits of this, and you'll see that doing it a third time is really no different from doing it a second time. There's really no value added, so you'll actually not ever be asked to do it a third time beyond this one. Okay, so if we plug in theta equals 0 to the numerator, we're going to get 0. If we plug in theta equals 0 to the denominator, we're also going to get 0. And so we're going to write out our limits separately. The limit of the numerator is 0, the limit of the denominator is 0, so we're going to apply L'Hopital's rule. Okay, and we take the derivative of the numerator and the denominator separately, and this first step is easy enough. The derivative of tangent theta is secant squared theta, subtract 1, and then divide by 3 theta squared. And we're thinking about theta approaching 0, and we're hopeful, and it's like, oh, I see that denominator going to 0. This is probably not good news. Secant squared theta, as theta approaches 0, that's going to be 1. Okay, so the numerator is going 0, denominator is going 0. I'm going to need to apply L'Hopital's rule again. Okay, and thinking about the derivative of secant squared theta, I'm going to have to use the chain rule. On the outside, I've got the square. So outside prime would be 2 secant theta to the first. Multiplied by inside prime, the derivative of secant theta with respect to theta, that's going to be secant theta tangent theta. So I'm going to have 2 secant theta multiplied by secant theta tangent theta, outside prime times inside prime, divided by 6 theta. And, okay, because tangent of 0 equals 0, and I've got that factor of tangent theta in there, this is disappointing. This is kind of bad news, okay? The numerator's going 0, denominator is still going 0. I'm still needing to use L'Hopital's rule. And so I'm just going to keep using it. I have faith that, eventually I'm either going to get, something good, or, I'm going to get something that'll show me that my journey is ended. Either way, I'm going to eventually get something, right? And so I take the limit of the derivative of the numerator and the derivative of the denominator. And now I think, looking at the numerator, I'm going to think of that as 2 secant squared theta times tangent theta when I go to take the derivative. But this will require product and chain rules. So this is going to be, like a derivative we need to think about. And derivative of the denominator, that'll be really easy though. And so I go in, I do it, and I'm going to get 4 secant squared theta tangent theta plus 2 times 4 powers of secant theta. And I think I'm going to actually not really get into that derivative in this video, because if you're interested in derivatives that utilize product and chain rule, you can go back a couple of units and watch me doing all sorts of those. I've done a lot of these examples. If you really just can't figure it out, I would encourage you to go to Wolfram Alpha or Mathway or something where it'll show you out the steps. Or just come see me in the morning. I'd be happy to take that derivative with you some other time. Okay, but if I plug in theta equals 0, okay, again, tangent of 0 is 0. So that first part of the numerator is going to go 0, but secant of 0 is 1. So if I take 1 to the 4th, that's going to be 1. I'm going to have 2 times 1 divided by 6. That will be 2/6. And there we go. I've got myself a limit. And that was, kind of a journey, but, 3 iterations of L'Hopital's rule. Not something to be scared of, right? It's kind of tedious, a little annoying on the derivative taking front. All right, number 11 has got sine of t over 1 minus cosine t as t is approaching pi. And so I'm seeing that is not, oh goodness, I had some wrong work. But we're seeing the numerator is going to 0, right? Sine of pi is 0. The denominator is not going to 0, though, because cosine of pi is -1, and I have 1 minus -1, which is going to be 2. So I'm going to, kind of like all of them, I'm going to evaluate the limit of the numerator and the denominator separately, and I see 0 divided by 2. Well, I take 0 divided by a non-zero. That's still going to be 0. There's nothing wrong with that. Okay, so this limit is going to equal 0. And that's really all there is to say about that. Okay, but I'm glad that I've got, kind of one of each of the types of examples. I made sure to go through that in the lesson as well. 0 and 0, 0 and non-zero, non-zero and 0. Infinity and infinity, right? All the different possible combinations. Okay, so as x approaches infinity, log x over the cube root of x. This is another one that we definitely talked about at the beginning of the year. We said that equals 0 because log x grows slower than any power of x. But if you were doubting me on that, you're like, I don't really have a good reason to believe you on that. Cube root also grows really, really slowly, and the graphs don't even really look all that different. They both grow, but, why wouldn't they grow at the same rate? You might ask. That would be a natural question. Okay, so what we would do is we would investigate using L'Hopital's rule. So we'd say, okay, numerator is going to infinity, denominator is going to infinity. This is a situation we can apply. Okay, so we're going to take the derivative of log x and get 1 over x, take the derivative of x to the 1/3 and get 1/3 x to the -2/3. And then if we look at that, it's like, okay, well, that would kind of looks like, I don't know, go to 0 over 0, I suppose. And that wouldn't be any good either. But what we could do is do a little bit of simplification first and get, an equivalent limit. The limit as x approaches infinity of 1 over 3 times x to the 1/3 power in the denominator. And this is a fraction whose numerator is staying constant and denominator is growing arbitrarily large, and that's the type of thing that's heading towards 0. Okay, so that's maybe a better reason to believe me on that. Okay, now the limit as b approaches 1 of b to the 9 minus 1 over b to the 5 minus 1. Okay, we're going to take the limit of the numerator and the denominator separately. They're both going towards 0, so we apply L'Hopital's rule, take the derivative of top and bottom separately, kind of reevaluate our limit. Look at this. Okay, this is looking much better. This is going to go to 9 over 5. Okay, number 14, 2 to the t minus e to the t over t. It's like, oh no, there it is. Okay, yeah, it's like it's L'Hopital's rule. I'm probably going to need another derivative of that, and maybe you're sitting there thinking, I don't quite remember. Well, this would be a really good time to start remembering the derivative of 2 to the t if you haven't started yet. Okay, so as t approaches 0, we're seeing this is going to 0 on the top and 0 on the bottom. So the limit of the numerator is going to be 1 minus 1, that's 0. The limit of the denominator, t is approaching 0, so t is approaching 0. Okay, we need to apply L'Hopital's rule. So here it is, it's time. You need to remember the derivative of 2 to the t. And 2 to the t is very close to e to the t. Okay, so its derivative is going to be very close to the derivative of e to the t. Okay, the derivative of e to the t is itself. So the derivative of 2 to the t is 2 to the t times natural log of 2 for the chain rule. That's really what it is. And so we're going to have 2 to the t times natural log 2, subtract e to the t, divide by 1. And so then I'm going to think about this, and it's like, okay, the denominator is not going towards 0. Okay, yeah, no, as the numerator goes toward, as t goes towards 0, the numerator is approaching 2 to the 0 is 1 log of 2. Okay, so that's log of 2 minus e to the 0. That's going to be 1. That'll be natural log of 2, subtract 1. And that's just some real number. I know that's less than 0, but not really all that concerned with that result. Okay, that's just the value of our limit. Okay, as x approaches 1, log x over sine of pi x. Okay, these are both going towards 0 as x approaches 1, so I'm going to show those separately. Okay, limit of log x is 0, limit of sine of pi x is 0 as x approaches 1. I'm going to apply L'Hopital's rule. I'm going to say, okay, well, I'm going to take the derivative of log x and get 1 over x. I'll take the derivative of sine pi x and get pi cosine of pi x. Think about x approaching 1, and I'll get 1 over 1 in the numerator, and pi times -1 in the denominator, and that'll be a safe place for me to stop. It's definitely, a form that I could recognize the correct answer in a multiple choice setting, or whatever I needed to do with that. The next three problems, they all work off of a table, and they're very similar to the problems we've already done. And, I worked this problem set ahead of time to make sure I showed all the work properly and had it laid out in a way that would actually show up on screen, because I knew that I was going to be, writing quite a bit more this year now that I was redoing this solution video, in light of knowing how these things are actually scored on the free response section. And having graded a couple of times, a couple of problems where I was like, oh man, my students, I don't know that I necessarily showed them the right way. Okay, I don't think there's all that much value added in these examples otherwise though, so I don't think you need to see me narrating me getting this process. I'm showing the limits separately, I'm applying L'Hopital's rule. On the one on the far left, I had to do it twice. Well, no, on 17 and 18, they only required one iteration, and there you go. Okay, I think that's going to be enough discussion. But this last couple of problems, these are a little more interesting, and so I think I'd give you this full treatment. So f of x is going to be the particular solution to the differential equation dy dx equals 2x plus y with f of 5 equals 0. And I am just going to point out, since you do know about separation of variables right now, that that is not a separable differential equation. F is not the type of particular solution we're going to be able to obtain in AP Calculus. And it's the type of particular solution, you just need to keep signing up for those math classes and take that differential equations class. You'll learn about the integrating factor technique. It'll be great. Really not that hard, just not part of our course. Okay, what we're going to need to do is we're going to need to be using dy dx to find like f prime of 5 and eventually f double prime of 5. I've worked this problem set before, and also I know enough about AP Calculus to look at this and say, okay, we're going to need the second derivative of y with respect to x. So we're going to start off by plugging in 5 and 0 into dy dx. We're going to get 10. Okay, so that'll just be telling me f prime of 5, that needs to equal 10, and that'll probably be useful on both of these problems. Okay, but over there on number 20, it's L'Hopital's rule. I can see the denominator is going to 0. I'm probably going to need to take the derivative of the top. That's going to bring in a second derivative. So I need to take the derivative of dy dx and get the second derivative of y is going to equal 2 plus dy dx. And you could say that's 2 plus 2x plus y if you wanted. Okay, but that's not really what we're here for, so I'm going to just find this value of the second derivative at that point, 5 and 0, so I could use that if I needed the value of f double prime of 5. And, I'm assuming that f is, either twice or maybe thrice differentiable, sufficiently differentiable to where the limit of f double prime of x is going to equal 12, right? Okay, I need that, but I'm assuming that, and it's not really assuming too much to assume that that's the case in this class. Okay, so f is going to be the particular solution to this. Okay, so this first limit, 3x minus 15, is definitely going towards 0. F is also going towards 0. And I know that for sure because if it's a solution to the differential equation, it's got to be differentiable, and so that means it's continuous, and that means the limit as x approaches 5 of f is definitely 0. Okay, so with no assumption, I can say this is 0, and that is also 0, so I need to use L'Hopital's rule. So I'm going to take the derivative of the top and get 3. The derivative of the bottom would be f prime of x. And I'm taking that derivative, or I'm taking that limit. It's like, okay, the top is, constantly 3. The denominator is going to be approaching 10. And so that limit would be 3 over 10. And for number 20, I'm going to have 10 minus f prime of x. Okay, well, that's going to be approaching 10 minus 10, which would be 0. Divided by x minus 5, also approaching 0. I need to apply L'Hopital's rule. Okay, so I'm going to take the derivative of the top and the bottom separately, and I would get the limit of f double prime of x divided by 1. Okay, f double prime is approaching 12. 1 is staying 1, so this limit is going to approach 12 over 1, and that's going to be 12. Okay, now that was a pretty robust problem set on L'Hopital's rule. If you did all 20 of those, I think you are plenty prepared for whatever quiz or test or assessment you've got on L'Hopital's rule coming your way. So that's going to be all for this video, but if you are interested, I do have extra practice problems for L'Hopital's rule. That'll be a separate video. You can probably see that in the suggested ones appearing right now, but that's all for this one. Thanks for watching.